Welcome to part 2 of lesson 3B7. In this particular part of the lesson, we're going to focus only on intervals of increase and intervals of decrease. This is one of the topics that you guys struggled the most with when we were looking at linear functions and lines. So I wanted to highlight it by making it into a separate little video. So in your notes it says that all the other characteristics that we've talked about so far are important, and we've already examined quadratic functions from the perspective of all of those other things. So interval of increasing we've looked at before with lines, but never with a quadratic. So the definition of interval of increasing is the domain over which a function has a positive rate of change. All that means is it's the domain over which when I drag my pencil from left to right, this thing is going up. It's getting higher on the pencil as I go. So when I go here, this line, the farther over I drag it, this thing gets lower and lower. So you can see that it's getting lower on the pencil. It's not till I get about right here that when I continue to go over to the left, this thing's gonna climb higher. So when I'm at x is -1 and then I move to x is 0, my y value gets bigger. So the section over which this is increasing starts right here where we hit this turning point and continues to increase across the rest of the life of it. So when we report our interval of increasing, we are going to give a domain over which it's increasing. We want the lowest x value where it's increasing and the highest x value. Well, the lowest x value for which it's increasing is right here at x is -1. Make sure you're not looking at your y value. You're looking at that x value where this turns and starts climbing again. So it starts climbing at -1. It stops climbing up here, but again, we've got arrows, so that really doesn't ever stop climbing. So our largest x value for which it's increasing is positive infinity. You will also sometimes see this written as just x is greater than -1 because this is increasing everywhere that x is bigger than -1. For this one, when I start dragging my pencil, well, let's go ahead and put in our shell x. Okay, when I start dragging my pencil, it right from the get-go seems to be increasing because the farther I go, the higher this thing gets, and it continues to go up, 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 up until we hit that vertex right there where it starts to fall again. So that means that for my lowest possible x value, go ahead and draw your little arrows that should be there. For my lowest possible x value is going to be negative infinity, because even though it looks like it happens right before 0, it really doesn't have a beginning. It's always going to be increasing from negative infinity up until this vertex value right here at 2. Okay? Notice that on both of these, the turning point happened at that vertex. So that value you choose for your vertex and for your axis of symmetry is going to come up again and again and again as you work through these problems. Okay, the interval of decreasing is very, very similar. When we're talking about an interval of decreasing, it's the domain over which a function has a negative rate of change. So basically that just means as I move from left to right, is the value, the y value of this function falling? If it is, then that is a part of its interval of decrease. So when I look at example 1, right from the get-go, this thing seems to be falling as I move from left to right. It gets lower and lower on my pencil there. So that means that when I write my lowest possible value where it's decreasing, it starts decreasing at negative infinity and it continues to decrease until we hit that vertex where it starts climbing again. So it stops decreasing when x is -1. Notice that these two are sort of the complement of each other. If it's not decreasing, then it must be increasing, unless in a parabola, it's doing one or the other. Okay, except for maybe at that little vertex right there where it kind of flattens out. But that's why we don't have an equal to in either place, because that's sort of a transition point. Also, remember that you could see this just written as x is less than 1, because that would mean the same thing. That's saying everywhere that x is less than 1, it's decreasing. All right, so let's look at example 2 then. We're going to have our x. We're looking for the lowest possible value where x is decreasing and the highest. So I'm going to take my pencil. We've already said that it's increasing at negative infinity, and it continues to increase until you hit that vertex when x is 2. So that means that the lowest possible x value where it's decreasing is at 2, and it continues to decrease forever because we've got an arrow there. So it continues to decrease to positive infinity. Even though it's pointing down, remember that we're looking at it from the perspective of the x value, and the x value is going to continue to get bigger and bigger and bigger because we're going to the right. You could also write that as everywhere that x is greater than 2, it's decreasing. Here, it's everywhere that x is less than 2, it's increasing, because when x is less than 2, you've got a positive slope because it's going up. All right, and that's intervals of increase and decrease. I hope that cleared up some misunderstandings. I'm going to pause it here and then come back and we'll talk about positive intervals of positive and intervals of negative.